First, thank you for inviting me to talk in this workshop. And really sorry that I cannot come in person because actually I prepared to come, and I have all the booking. And but a few hours before the flight, I discovered that my travel document is out of date, so I have to cancel everything. So.
So, Shengwei, would you mind, as you make your screen or your slides full screen here, would you mind just starting with a brief introduction of yourself for
Yeah.
those of us who may not know you?
Yeah. Yeah. And yeah, I'm working now in the Hong Kong Polytechnic University, and I'm leading a research institute called Research Institute for Smart Energy. And I'm also a chair professor of building energy and automation. So let's first let me introduce a little bit of our research institute for smart energy. We call ourselves RISE, and this is a cross-disciplinary research platform in the university for developing innovative energy technologies and sustainable and carbon neutral solutions. So in this research institute, actually, we have 5 main focus areas, including district energy system and smart grid, and the smart energy and smart energy systems, and advanced energy storage technology, and advanced renewable energy conversion technologies. And we also have a team of advanced energy materials. So actually, we have close to 70 professors and faculty members from 11 departments in the university. Now, so let me move to the main parts of my talk. So now, in the last decades, when we talk about build automation, we move from automatic control to smart control and management. And if you have a look on so I move a little bit because I need to see the whole screen. Right. And so we talk, if you have a look on the building control tasks and challenges and opportunities. And so, first is the control performance objective changed. We have more challenging control performance objectives. And the building automation technologies, including hardware and software, are developing, and that gives us the hardware and software side is more capable and powerful. And in terms of the building facilities, energy systems also changed. Now the systems and the functionalities is much more complex and powerful. And another thing is service objectives and the boundary environment are also changing. I will give you a little bit because the expectations and the automation system, building system actually serves a bigger, and our service scopes are actually larger. So have a look on today's typical architects of building automation systems. So I call it third or the fourth generations of building automation systems. Basically, you'll find in terms of architects and the configuration of architects is even simpler compared with the automation systems and 20 years ago, because now basically it's the IP technologies, the internet technologies make our control networks simpler in terms of the architects. So let's have a look on the implementation of the control strategies. So we can have a look. Now, in terms of simple and control logic and low computing load, the control strategies with a simple logic or low computing load, and those strategies can be implemented in those network stations, even in the field DDC controllers. But for those advanced control logics involving extensive computing, software not involving more extensive load in terms of programming, in terms of computational load. So we have to implement them in the central stations or even in the cloud stations. So that, because of that, large-scale online optimization control cannot be deployed in the field level. And the control of only very few systems can be optimized, because if we cannot put it in the low level, in the field level, then there are many limitations for the control optimization of subsystems. And another thing is many disputed computing resources are not effectively used, because actually in the field level, we have many computing resources in the building automation or the smart building systems. Particularly nowadays, the IoT applications, many IoT devices are deployed in the in buildings. And another thing is the high implementation cost we still face today. So now new expectations and functionalities for today's building and the future buildings. So if you have a look at the functionality of building automation systems, for the conventional functions, including sensing the system states, ensure the system health, and optimize the system control, those are the conventional. But now we face in the new tasks or challenges that including such as the attention of individuals and the components. So we are required to pay more attention on the individuals and individual users and the individual components. And we have to coordinate the system at the field level. And another new challenges or the tasks we face is the integration with power grid. And because today's building and the future buildings not only take powers, but we also have to contribute and interact with the power grid to contribute to the power balance and the reliability of power grid operation. And so let's have a look on the development and opportunities for smart building technologies. So now you see in terms of hardware, so we have more emerging hardware platforms and technologies, including IoT, and wireless networks, and smart sensing, and so on. But in terms of software, we have more powerful and data and software technologies such as artificial intelligence, and two colleagues discussed about this just a few minutes before, and advanced data and optimization technologies tools. So we have better hardware and softwares, and we have the better use of those technologies to enhance our control systems. So here, let me show a little bit, a few examples of an efforts in our team on advanced HV system control and control optimization. So I made a summary of our work in this area, and basically we concern more concerning poor quality of online management. And we concern the robustness and the sensitivity of control strategies against the management uncertainty and challenges of working conditions, and effective and robust online optimization technologies. And we pay attention on the adaptive optimal control using AI-enabled online adaptive models. And we develop smart control for energy systems interacting with smart grid to unlock building energy flexibility. And another area where we work is distributed control optimization technologies based on the failed IoT networks. Here in the following, I introduce a little bit of these efforts just for sharing. And one project we are working is the development of next generation key technologies for smart building. So this is the summary, and basically we do it in two approaches. One approach is distributed intelligence for real-time optimization. Another is effective big data analytics. So we work in three levels. One is fundamental technology, that is about dynamics of the integrated energy systems. And the second layer of level is fundamental technologies, that is basically distributed real-time optimization and big data analytics. And in terms of application technologies, we developed health monitoring and diagnosis technologies and real-time control optimization technologies. So let's have a look on the distributed optimal control strategies being developed on IoT field networks, and with a summary of the challenges and tasks. One is how to decompose the optimal optimization problems, the large optimization problem, to small problems that can be handled in distributed IoT devices. And the second is the effective and robust online optimization algorithms. And the third is the convergence rate enhancement methods. And another is the delay tolerance schemes. But that is, so we talk about the information, the data transfer delay over the IoT network. And another thing is event-based optimal control schemes for power saving of the wireless networks. And so this is the work we did to develop distributed optimal control strategies for the IoT field network. And this is the example of what we did is distributed real-time optimal control strategy on the deployed on BAS field control network using IoT sensors and drivers. And basic approach is actually we decompose the big optimization problem into a number of small and simpler problems, and to deploy those simple problem into single individual IoT devices, and then we coordinate this this optimizing problem in individual IoT devices, and then we locally, and then we that is to distributed optimization over the IoT network. And actually, you can find that we in this area we actually published a number of papers in the IEEE journals, such as the internet the journal of IoT journals, right? And another thing work we developed while working is the field level IoT based control implementation and optimization. So here is basically, I assume that in the future, today, we still very much use the DDC-based field level control. That means the sensors and the drivers for one sub-process are connected to one DDC controller. And then the control, actually the sensor and the actuators are connected to one DDC, so we do not have the close network issue for control, for process control. But in the future, if we want to have the IoT sensors, such as IoT-based smart sensors and smart actuators, which are fully used, then the sensors and drivers to form up the control, the hardware will be actually connected through the network. So in such a case, how we can develop the robust stable control close the network? So this is one issue. So actually in this area, we developed those IoT-based field control control architects and topology using Wi-Fi and 5G cell networks for HV process control. And so in this area, actually, basically, we solve the problems to make the robust control and the stable control of the HVAC process, which was not a big problem if we use the sensors and the drivers connected with one DDC controller or digital controller. But if we now the sensors and actuators are connected using the network, so that is the issue. So we have to solve this problem of the data transfer and unstable transfer of data, and make sure the stable control and the robust control of the building process over the network. And another task, the work where I can show is the control of air conditioning system under limited cooling supply. So this is particularly in the case if we interact control the buildings interacting with the smart grid to support the reliable operation of the power grid. So we have a look on the comparison. We have a comparison of conventional process control, and our conventional feedback control is demand-based feedback control, and although we do not talk about this name, we just talk about feedback control. This is in that case because the supply is always sufficient, and so the control system just take as much as we need. So just based on the demand. But this is the current situation. This is the past situation. But in the future, because our power systems have full of the high penetration of renewables, and the power system supply demand balance is a big challenge. So they need demand side to contribute to help them to make a better to keep a healthy balance and to have the renewable operation of the power grid. So in such a case, in many cases, we need to control to limit our power consumption, and to do so, we need to limit our cooling supply, such as the chiller operation. So in such a case, if the conventional feedback control system will not work, because our conventional feedback control system is based on the sufficient cooling supply, but on the insufficient cooling supply, and so the control system, the control logic will not work properly. So actually, in the buildings, there are typically 3 cases we have this problem of limited cooling supply. One is demand limiting control, as I mentioned. Another is the morning start. In the morning start period, because particularly in the hot areas, such as in Hong Kong and I think part of states, and in the summertime, or such as in Hong Kong, we have half a year. In the morning, the starting period, the system is rather hot, it's a high temperature starting. So in that time, even we start many chillers, then the cooling supply is not yet not sufficient. So that time, the morning start period actually face a situation that is the cooling supply is not enough. And another case is the soft stop. Actually, if we run the chiller plant till the end of the working time, so actually it's not a better way to save energy. We can shut down some of the operating chillers earlier, but when we shut down some of the operating chillers before the working hours, and actually the cooling supply is not sufficient, it's limited. So in such a time, if all the feedback control is still based on the conventional feedback control with the assumption of sufficient cooling supply, actually the different control loops will bid for the limited resources, cooling supply resources, then there will cause the problem of uneven distribution of power supply. So to solve this problem, actually we developed two generations of control strategies for that. The first generation of the we developed the supply-based control, and here in the PowerPoint I show is the first generation. And but the problem of the generation system is that this cannot be directly implemented to the DDC controllers, because we need to they need a little bit higher computing powers. So it's not so practical to be implemented in the buildings with DDC controllers. So therefore, we developed the second generation of the system. So we developed a control logic called reconfigurable feedback control strategy, which can be deployed on conventional DDC controllers. And so that basically what we do is we use two controllers, but share one the same PID controller. So in one PID loop is the conventional PID loop that is based on we control base step. That is what we did as normal. And in the second case, if the control if the supply is limited, so we switch to another control loop. Then in such a case, the control is not to control the process output set point at a fixed set point, but instead the objective goes to control the return temperature of different zones to be an even temperature. This temperature will actually slowly increase because it's not a fixed, it's slowly increase because the cooling supply is not enough. So the temperature of the space will increase, right? But we will control that means the set point of this set of the control will increase slowly, but with even set point increase. So that is actually we cannot control it affect fixed set point such as 23 degree or 24 degree, but we control the temperature of the spaces in the building increase slowly and evenly. So that is the objective. So this is implementation of the strategy actually in that is for the control of air chills. I do not show the details, but you can find actually there's a patent applied, and there's also one paper published. I think is a couple of months ago. If you want to have details, you can find this out. And actually, these strategies we are actually implementing these strategies, full-scale implementation of strategies in the new commercial complex development in the Kowloon high-speed train station. So this in this Kowloon train station, on top of this station, there are 4 buildings under development, and the totally this is a very large commercial complex. So the total floor area is 0.3 million square meters. So actually, we are implementing these strategies in all the DCG controllers in that building. So we use we incorporate with the developers, develop the smart, energy efficient, and energy flow buildings in this development. And another work I like to share is the smart control of HV system with of enhanced building environment control performance for providing frequency regulation service to smart grid. So actually, also very simple to highlight, you know, in the power grid, but this regulation is actually implemented in some states, some power system in states, but not yet in Hong Kong. And they are discussing these implementations in the mainland of China. So you can say basically the power grid send a signal called automatic generation control signal to ask the power the demand side such as buildings to change our power use, the energy the electrical power use according to the needs of power grid. So they ask us to use more and use less, depends on the needs of frequency regulation. So this signal changes is in terms of seconds and minutes. So actually, we developed you know, in buildings we have many those variable speed drivers such as variable speed fan, variable speed uh, chillers and pumps. So we can actually control our data, our energy use of those devices to follow the needs of the power grid. But then what is the problem is that the first we developed the strategies to to change the power use according to follow the signals, and this is not a big issue. And but we find in such a case we find our environment control, such as the temperature control of the buildings, is much affected by this regulation. So then we say, okay, because this regulation, this is actually a disturbance to our building environment control, that is basically space temperature control. And this disturbance is generated by us. So then I asked my student that why not we use this disturbance to have another composition of the control. So that therefore we develop a strategy called frequency disturbance composition. So in such a case, originally, if we just without introduce this strategy, actually the temperature, the supply temperature to the spaces actually can change 4 to 8 degrees, right? It's such a degree Celsius, right? And so that is what actually caused the temperature in the space vary too much. But after we introduce this frequency disturbance composition scheme, actually we can reduce the supply temperature to space, reduced to around less than 2 degrees. And you know, for 2 degrees variation of the temperature supply, and actually do not cause too much disturbance to the temperature control of the space. So therefore, and another issue is actually because of this compensation scheme, we also reduce the valve movement. So that is the valve movement will be also reduced. So that helps to reduce the wiring potential of the valves during the control. And finally, I like to show a little one of the examples I like to share is what is the energy benefits of introducing optimal control in buildings. Right. This is one of the particular example in the clean room air conditioning system. So that is actually used for the medicine production. So this is a very interesting case. And this project actually, I was invited to investigate the case. All the control systems, air conditioning systems are already upgraded and developed and installed. It's a quite a nice designed air conditioning system for the medicine production clean rooms, and the automation system is also very very good automation systems, but the energy consumption is too high. So therefore, we help them to develop the control logic, and eventually we introduced a strategy called adaptive full range decoupling validation control strategies for the clean room air conditioning systems. So this is basically we optimize the system and optimize the, or in this particular case, for the strategy we can introduce to optimize the system and optimize the control. But in this particular case, as I mentioned, because the air conditioning system is already design installed, and the control system is design installed. So what we can do, we do not change any hardware of the ventilation system, actually air conditioning system. We do not change any control uh, hardware, including sensors, anything not changed, but only change the software of the control. And this is the test. So you can see the blue ones is the original control strategies, and the right bar, there is the energy consumption of the original control strategy, the blue. And the red bar is the energy consumption after introducing the new control strategies. So you can find actually the energy saving, annual energy saving is about 4 million Hong Kong dollars. It is about 42% of the energy consumption used. But this is not only for electricity, but also for the gas, because they consume gases for hot water production. So this is a good example that, of course, in the commercial buildings, normally purely for introducing optimal control, we cannot save up to 40%. Is difficult. But in these industrial buildings, fully introduce optimal control can actually have such a big energy saving. So in summary, smart technologies can offer great benefits to buildings in terms of energy efficiency, service to users, and the power grid and facility management. And evolution of building energy systems, and service objectives, and boundary environment and performance objectives provide great challenge and opportunity. It's a great challenge. It's also opportunity for smart control research and development. And emerging IT hardware and software technologies provide great opportunities for enhancing building energy performance for further research and development. Smart control technologies for buildings need to be developed in responding to those evolutions. And finally, I like to, based on my experience and my knowledge and experience in research and also the implementation. So I have a few points to discuss here. And one thing is concerning the adaptation of emerging technologies, and so what are meaningful technologies, in what applications they are beneficial? For instance, digital twin. For instance, data-driven models and artificial intelligence. For instance, big data. Because of course, in terms of research, this is a very meaningful and this is very important area. We got to pay efforts to develop the technologies to make these technologies to be useful, to be practically useful to in real systems. But we got to, we need to think about just it's not just to introduce technologies to buildings, but we need to think about what the benefit, where we actually need it, because in some of the or many of the applications we already have some mature technologies which actually can provide us rather very good performance. But in some areas we not yet have good solutions. In such a case, then those technologies, if can provide better performance or good solutions, so that is the area that we need to pay efforts, but not just to bring those hot technologies in our systems, which may not provide benefit to us. Another, so that sense is still do we still need physical technology and the domain expertise and and capable AI. But what's from my point of view, I think, as I mentioned, as the earlier expert also mentioned, that AI applications need to integrate with the physical knowledge and human expert knowledge, and so that should be the future. Not in the real application, and I find some information the technology provider, they do not have any don't have sufficient knowledge on building energy systems, and so they just purely playing on the data, and in buildings, particular commercial buildings, the data is very limited. So we based on the data. So actually, purely based on data, is very difficult to provide us good solutions and reliable solutions. So I take an example of channel control, AI-based control. I see many of those AI-based channel control, and actually many of those control logics I find in a real system it doesn't work. Because the one reason is what are the optimal targets, the optimization targets, and what are the accuracy and the robustness of AI-based learning and decisions. And because if we purely use AI, so it's very much based on the measurement accuracy and the robustness of measurement. But our measurement is not enough. It's not accurate enough in real buildings. So then, if the outputs purely based on the AI cannot give us because we are talking about energy saving of 3-5%. But the data accuracy cannot provide us a difference of 3-5% of accuracy. So it's very difficult for us to find out a better solution or accurate solution, optimal solutions purely based on the AI, and this AI is purely on the data. So that is the example. And so for the channel control, another thing is model predictive control in many cases, model control. But model predictive control actually, in some cases, it is useful, but not all the cases, because in the normal operation of the chiller plant, I'm talking about chiller control, right? And in the normal operation, it's basically the system is rather stable. So if we base on the actual measurement, the load measurement to control the chiller sequence, it's more reliable and more accurate. But when the chiller, the predictive control is useful, because in the cases that we need to predict the load in the future, such as in the case if the scheduling involves the storage, for instance, there's cold storage involved. So then we need to prediction is useful, is needed. Another is morning start. Morning start, you know, the actual measurement of cooling load is not a real measurement, the real load, right? Because it's in such a high load condition. The actual load, the actual measured load is actually the capacity provided. It's not a real load. So in such a case, if we want to have a better control, we may need to actually predict what is the actual load. Another is soft stop. So those are the things. So basically, I do not go to details, and I'm happy to discuss with you on those issues because nowadays the AI and data, the data technologies and this technologies, very much efforts are paid on this area. But now it is the stage actually we need to think about what type of AI technology and what of the data-driven technology are actually needed and actually can provide the real benefits to building control, building operation. So that is what I'd like to share with you. Thank you so much.
All right, thanks so much, Shengwei. Another big round of applause in the room. I don't know if you could hear lots of appreciation for your work, which is very thorough and covered a wide range of really interesting topics. So I guess if folks online have questions, I'd invite you to just unmute and go ahead. But are there any questions from the room first?
Hi, thank you for the presentation. I thought it was very interesting. I wanted to ask if you had to name an IoT application for commercial buildings that presented the highest opportunity, what would that application be for IoT edge devices and IoT technology?
Yeah, and actually, IoT now is very much popular, and for the moment, my understanding or my experience is to say is it helps us to provide additional low-cost monitoring, such as environment monitoring, power monitoring, and those things, and to supplement the the conventional building automation systems. So this is very successful. But if you have a look on the IoT technologies in commercial buildings, so actually the control functions is not much used. It's basically we have the IoT data collection, use IoT sensors and send this to the central stations or to the cloud, and then we can make some data processes and to help us to make decisions, but mostly cannot be directly used for control applications. So in the future, if we want to have a more widely use of IoT technologies, and as a mainstream technology, as today's building automation system, so there's a few issues we need to handle. Is one thing is the how one thing is that how we can use the, as I mentioned in our research, how to use this distributed computing resources to support control optimization. That's one issue. And actually, this is in the computer area, such as edge computing in the area. But of course, the edge computing in the computer area is the top of edge could be a little higher level. And the talk about edge computing resources, maybe the PCs in different area of the network. But in our case, we are more more edge because we talk about the computing sources in our IoT sensors and drivers, and these resources actually can make it more effective use for optimization. Another is, as I mentioned, is because if we want to allow the IoT devices, those smart sensors and smart drivers, the actuators, can perform the typical process control, right? Because process control in buildings is one of the very large, is the main, one of the main functions needed. So we need to use those smart sensors and smart drivers and integrated over the network, wired or wireless network, to perform the feedback controls. This is one area.
Okay, great. I have another question for you, which is a little bit less around technology and more around deployment. So if you imagine a future where maybe the kinds of technologies that you're talking about have been deployed in, say, thousands or even millions of buildings, and thinking specifically about the sort of East Asia context, what does the pathway or pathways look like from kind of going from where we are today with the technology to that future of widespread adoption?
Yeah, so actually in my mind, but it's not yet practical. In my mind, is in the future, just like today for all human beings, for people, each of us have one mobile phone. So when we have the mobile phone, if we then when we are forming a group, then we can actually exchange our contact, right? Such as in the States, we use the WhatsApp, right? We will have the working group and we have the information exchange, then we can make decisions. But in the future, for the IoT devices, that is every devices, this electrical and mechanical devices, are actually embodied with a smart device. Like today, each people have an iPhone, right? So in the future, each mechanical electric devices will have a IoT smart device. So one way those devices are integrated to form an energy system. So then we don't need to have, like today, have the BMS today to have the sensors and accurate contact, because each of those mechanical devices, electric devices, already have a smart device. We can build up, connect these smart devices and to build up the control systems. So, and of course, in the higher level, we may have some another central management. So then this is the way. And if to do that, then we one of the very basic functions today we can easily handle in DDCs. So that is the feedback control loops today is ready to handle in DDCs, because all the sensors and devices for one control process are connected to one DDC controllers. But in the future, and the sensors and driver, the actuators are not connected to one controller, but they are connected over the network. So this is something we need to handle. But I think we did research, but I find it's not yet mature enough for practical for the convenient wide application. Is the early steps of this effort.
I see. Thank you very much for that perspective. Do we have one last question for Shengwei before we break for lunch? Nothing online? Okay, great. Well, thank you again, Shengwei. We really appreciate your time and sharing your expertise. And thanks again to all of our speakers from this morning. We have lunch waiting for us upstairs in the same place as we had breakfast. We'll reconvene here. Talks will start at 1 for folks online. So we have a 55-minute break here. And then maybe we can try to be back in the room around 5 minutes before that for in-person folks. Yes. Oh, I'm sorry, Gregor, please go ahead with your question or comment.
Oh, yeah. I had wondered if Shengwei Wang could paraphrase one more time his position on what type of physics knowledge do we need in the future, and what the respective role of AI and physics should be. I think we heard some opposing views in the room today, but do we still need physics-based expertise in the future?
We do need physics and expertise. That is for sure, because I observed many of the technologies and many of the research, and they think just data in, decision out. But in this case, it's mostly it's rubbish in, rubbish out. And I gave you one example, because our data and our system actually have those physical, there's some logical relations between the data. So now today's those data technology is very powerful, but in the buildings there are so many variables. If we do not make the use our physical knowledge, use your domain knowledge or the expertise to tell the tools such as AI. So what is the relation? So which outputs are affected by some inputs? Even those are the very simple relations. If we do not tell them, so there are too many variables, and the AI cannot actually find out their correlation. It is very difficult.
Yeah, even though there is effort on causality detection, right? I mean, there are a lot of technical systems where causality inference is being applied, and they are making progress. So I wonder how we feel about this in 20 years from now. But that, I don't want to keep you from lunch. You're all hungry now. So thank you for your comment, Shengwei.
Thank you. Thank you. Bye-bye.
Okay, great. I think that's a good place to stop. So we'll see you back here a little before 1 p.m. Thanks.